So in our house, it's got like the science theme going on, and in the kitchen we have one of the signs that says, chemistry's like cooking, but you just don't lick the spoon, right? And so, cooking is like chemistry. Cooking is like chemistry, but just don't lick the spoon. You can, in chemistry, but you can lick the spoon in cooking. So one of the things that, if you're like me, I'm amazed at, if they are alike, and they are similar, cooking and chemistry. In chemistry, we're real careful about, all of this will react if you have just this certain amount of this, and it's more, it has less forgiveness than cooking. Because right here we've got A through E different recipes for making chocolate chip cookies. And you can kind of see a varying amount of flour, sugar, butter, baking soda. And so they have different properties. And depending upon what kind of cookie you might like A, or you might like C. All right, on to the next part. Part 2. There you go. So a few chemistry things I want to link to cooking. And we start out with this example. I'm going to go ahead and make this process of making a sandwich into a chemical equation. So it looks like this. We are going to make cheese sandwiches. For every one cheese sandwich I make, yep, one cheese sandwich I make, I'm going to need, I'll just put 2 slices of bread, and we're really cheap here, 1 slice of cheese. Goodness gracious. So, underneath that, we have some, I call HAVE, have information. So what we have is actually 16 slices of bread and 10 slices of cheese. So the question is, how many sandwiches can we make? We can only make 8. That's right. Answer, you can only make 8 sandwiches. Why 8? What's that? Like a hot dog.
I want more than 1 plate.
Yeah. Well, we're going with this. This is what we got. But the reason you said 8 is that we are going to run out of our bread first. Here in a minute, well, I guess you would say that our bread is limited. Okay, and our cheese is excess. Cool. You got it. So what's left over? How much cheese is left over? 2. Yep. 2 slices are left. You got it. Exactly. So in making a sandwich, you have a choice of 1 to 2 to 3 to 4 slices of cheese. But in chemical reactions, molecules, they are very specific. You guys, earlier on in the course, you balanced equations, remember? And you put numbers, big numbers to the left of species to say how many you would need and how much would be formed. And to me, those, what we call coefficients, or strict measured coefficients, are kind of like my 2, 1, and 1, the same relative amount. Okay, so in chemical reactions, we often have something we're going to run out of first, and that is what we call the limiting reagent. In this case, our bread was limiting, so that was our limiting reagent. The other one is what we say that's there in excess. Now, if you have 3 ingredients or 3 reactants, then probably still 1 is limited and the other 2 are in excess. Very good. So you're going to have to pick on both of you guys here. We have several of these your turns. We're going to scale up this recipe. This recipe is supposed to make 25 cookies, but we're going for 100. So I'm going to go back and forth between you two. So Autumn, how much butter would I need? 2 cups. And how'd you get it? Yep. She took a half cup times 4 because we're scaling this up 4 times. Exactly. Okay. Taylor, how many chocolate chips would you need? 4 cups. 100 cups? You must like chocolate chips in your cookies. Okay, Autumn, how much brown sugar? 2 cups. Very good. Taylor, white sugar? 2 cups. How many eggs? 4 eggs. 2 teaspoons. Okay, 1 1/4. 5. Good job. 5 honking cups of flour, which doesn't seem like a lot for cookies. Taylor, how much baking soda? 3. I'm liking it. She took 3/4 times 4 and she got 3 teaspoons. Awesome. Autumn? 1 teaspoon. Perfect. Very good. And are you like me? Sometimes you like scale something and you don't rewrite it or anything, and then you forget to double something. Hate that. Very good.
I can't make cookies that taste like flour.
The cookies taste like flour? Have you thought about just not putting in as much flour as it says?
You need more time to
Need more chocolate chips? You said 100 cups of chocolate chips? Woo! That's crazy. Okay, so switching gears to quesadillas. Let's go ahead and write this. I'm going to say, I can't remember, who did I leave off on? Was it ready for Taylor?
Yeah, I didn't.
Okay, so Taylor, read the thing a few times, and what would I write as reactants and products for this? Perfect quesadilla can be made with 2 large flour tortillas and 1 cup of cheese. What's my product? It is the perfect quesadilla. And so I'll just put a Q for quesadilla. 1 perfect quesadilla. So what are the ingredients? Or what's the reactants? 2 flour tortillas and 1 cup cheese. Cool. Oops. Right. So we open the refrigerator and we have 350 grams of cheese. It's about to expire. How many cups is that? That is 7. It is 7. Very good. So drat. I don't know where. Maybe I have room down here. So we need 2 flour tortillas and 1 cup of cheese going to form 1 perfect quesadilla. So you told me cheese-wise 350 was 7 cups? Cool. Okay, Taylor. If we use all the cheese, how many quesadillas can we make? Yeah, 7. I agree. Next question. If we have 8 tortillas, which ingredient will be, this is for you, Autumn, which ingredient will be completely consumed? And this will be left over. How many tortillas do we have? We have 8. Oh, 8 tortillas, and we need 2 tortillas per quesadilla. You'll have cheese left over. We'll have cheese left over. Yep. So then, which is, Taylor, which is the limited supply? Which is in limited supply? So this one is excess. Yep. Tortillas is limited. Yep. You got it. That's it. We do that in chemistry too. Oops. Okay. So this right here, we're going to use in a minute. So we're going to come back to this. This is just a figure from your textbook, and it reminds, your textbook points out that in some cases you can buy these kitchen scales. You can buy kitchen scales, and in some recipes they tell you mass and not volume. We're mostly about volume here with our recipes, but mass kind of makes sense because sometimes things are fluffier. Like I think your textbook uses this example, like packed sugar. Like how well you do pack it, you know? So we are going to use these for the next year turn. We're going to focus on the flours, these guys, not cornstarch, but these 4 flours, and we're going to knock out densities. So on the next one, and I'm actually a little bit easier than what your textbook says. Remember, the symbol for density is this looking kind of, it's the Greek letter rho, that's density. Density is mass divided by volume. And in this case, your turn, what I want to do is take this mass and divide it by that volume. So, whose turn was it? Okay, Taylor, what will the units of our densities be then? If I take this mass and divide it by that volume. Grams over cups. Yep. We're going to end up with grams over cups. Yep. Perfect. So, Autumn, what would the answer for the first flour, the all-purpose plain flour, what would its density be?
91 grams per 1 cup, 120.
Yep, 120 grams per cup. Perfect. What about the cake flour? Taylor. What would the density be for the cake flour using the previous slide?
So I guess that's 130.
Oh, 130, yep. Wait, yeah, 130. Okay. So what would the next one be? What's the cake flour?
130.
Yep. Autumn, what about the next one?
130.
Taylor?
What?
What about potato flour?
Is it half a cup and a tablespoon? Yeah.
Well, so the half a cup goes with 80 grams, and the tablespoon goes with 12 grams.
So for the half a cup, 40 grams. 1 cup.
Well, if you're going to increase it, then you're going to increase this cup too. So you doubled it to get 1 cup, which is fine. But then if you double one, you double That's what I think so too. Yep. It's dense, right? It's the most mass per volume. So all flours are not made equally. Very good. So this cute little water molecule, we talked about water in chapter 8. And we talked about how it is so awesome because it has hydrogen bonding. Do you remember, Autumn, anything else that happens? So we can get hydrogen bonding with hydrogen and oxygen. What are the other 2 ways we can get hydrogen bonding? If hydrogen is a part of, here's oxygen. Hydrogen is bonded with what?
Hydrogen bonded with oxygen.
That gives you hydrogen bonding. What else? What other conditions can you get hydrogen bonding?
With F.
With F, yep.
And N.
And N, yep.
I only know that because you're pointing at
That's okay. And that's important because we have a lot of, in DNA and RNA, we have, guess what the N stands for? DNA and RNA. Yes, it is. Yeah, it's not nitrogen. But there's a lot of nitrogen. It's not nitrogen. It's okay. So, but anyway, there's a lot of nitrogen in it, and so we have hydrogen bonding because of that. The proteins have a lot of nitrogen.
What is it about those three that is it thinking about them?
Well, yeah, because they're small because they're just small. They aren't very big atoms. And then the other thing is they're very electronegative.
Oh,
So we said
what are the
electronegative.
most-
Yeah, increases because they're very electronegative and very small.
It increases until you get to those gases.
Right, these guys, yeah.
What are they? They're not.
They're electronegative. They're like neutral. They're zero. Yeah, yeah. So we're going to talk about cooking here, and a lot of times we just cook in water. Cooking is good. Cooking is good. Sorry, water is good in in the kitchen. One of the reasons water is good is because a lot of things dissolve in it. But now, like dissolves like, is water polar or non-polar? Okay. Do you think it's polar or non-polar? The opposite of water, the one that's the other one, is oil. And to be polar, it has like a kind of a partial negative or positive. That makes it polar. It is polar. Water is very polar. So like dissolves like, so polar things will dissolve in it. The other thing I want to talk about, I mentioned, kind of alluded to it, it's a good way to cook things because it actually is a crazy sort of thermal properties going on. It takes a lot of energy to make it transition from a liquid to a gas and from a solid to a liquid. And then the other thing is it retains its heat. And that's related to its hydrogen bonding. Okay. So we can kind of think of the energy at the melting and boiling point. It's easier to show you. So this is a temperature diagram. Sorry, up here is temperature and versus energy added. So think of this as kind of time. Think of this as you have an ice cube. You're going to add heat, and that ice cube is going to increase in its temperature. And when it hits, what is the melting point for heat? I think what's the melting point temperature of water? 30. It's funny. Some places I bet it is 33, but it's usually we say 32 Fahrenheit. That's
like the freezing and the...
Yeah, it's both. Freezing and melting, it's the same temperature. Yep. Yep. Freezing and melting, it's the same tipping point. So what is 32 Fahrenheit on a Celsius scale, Taylor? Oh. 0 degrees Celsius. Very good. So, Autumn, what temperature does water boil at? 100.
Or
100 degrees Celsius, or 212? 212 Fahrenheit. Yeah.
how do you think that?
I would have to Google it, but those I have memorized. It's like a 5/9 or a 9/5 and a plus or minus 32. Are you Googling it?
Yes. It's just like different kind. So if you go Fahrenheit to Celsius, you times it by 9/5 and you add 32. Or if you go Fahrenheit to Celsius, you go, I guess that's 1.8, times about 1.8 and that's 32.
Okay. Jot that down. Did you get that, Taylor?
Fahrenheit to Celsius is times by 9/5 well, Fahrenheit. What's Celsius? Fahrenheit is equal to the temperature in degrees Celsius times 9/5 plus 30. Yeah, so Celsius is a whole lot less.
So Celsius just makes a whole lot more sense.
5/8 minus
5 nights.
5 minutes.
Is that right?
Or 9/5.
This one?
Oh, yes, okay. Oh, you're right.
Like if you go into the ER or whatever, the nurse will have it listed for whatever reason, Fahrenheit, Celsius. I don't know why they do that.
Anyway, I want to go and they weigh you and it's in like
Yeah.
unit, and they're like, "You want to see it in pounds?" I'm like, "No."
So we have an ice cube here, and we are colder than 0. So the first bit of heat we give it is going to just bring it up to the melting point. And then the next bit of heat we add is going to melt it. Okay? And then it'll be liquid. And then the next bit of heat we add is just going to take it, it's going to stay a liquid, and it's going to come out at 100 degrees Celsius. And finally, the next bit of heat we do is going to turn it into a gas, evaporate it. And then once it's all gas, the next heat we add will increase the temperature of our gas. So think of it this way, when we use water to cook, we are, let me see if I get this right. Basically, when we use water to cook, we're basically we have the water at the boiling point temperature and it just sits there. Well, I say sit there. You can't see it, but of course, if you have your boiling water too long, your water's all going to boil out. But that probably doesn't happen. So for the most part, you're just humming at 100 degrees Celsius. That's one thing I think is interesting. You can pump it, you can jack up your temperature, but until it all evaporates, we kind of think of it in terms of it stays there. But it'll evaporate fast. Yes, it will evaporate more quickly. Exactly. So we kind of have a limit to the temperature we can cook at with water. It's 100. So there are ways around that, though. You may or may not know this, but and the word is external air pressure, boiling point external air pressure. Well, so in order for something to boil, okay, if this is my liquid, in order for it to boil or begin evaporation, this vapor pressure of this liquid has to be equal to the vapor pressure of the atmosphere. I know that sounds weird, but the vapor pressure of the atmosphere is this. We just talked about this in meteorology.
So that's why I keep the lid on it.
No, I think if you keep the lid on, you're kind of what you said, you're
building
more.
more pressure.
Yeah, I don't think our lids aren't pressurized. Our lids aren't pressurized. So the deal is if we go ahead and climb a mountain, what happens to the pressure when you go up in elevation? Yes, exactly. So at higher elevations, I'm going to take some of these away, and your temperature is going to be less. So in other words, if you go up to Colorado, and you have a thermometer with you, your boiling point temperature of your water is going to be like 97 degrees, not 100 degrees.
That's why I could never get an egg to cook all the way. A hard-boiled egg.
Yeah, 3-minute egg would be different there. Yeah.
3 minutes?
Well, no, like a 3-minute egg, you'd have to go longer.
How long do you guys take to boil egg? I thought it was like 10 minutes.
I have to call my mom.
Yeah, I asked my
husband.
Like 15 minutes.
I think it's 18. I think we go 18. Yeah. So water will boil at lower temperatures at higher elevation. Sometimes, like on box mixes, they will give you your instructions, and then we'll say at high elevations, and it will give a higher, either longer or higher temperature. So, and the word there is longer cooking times. And then the figure from your textbook's interesting. China, mountainous, right? China drinks a lot of tea. What's that do then? But what this is showing you is actually an assortment of teas over here. Not over here, over here. So for instance, at this elevation, which is lower, they have temperature boiling at 97, black tea works well. You go up in elevation, and your boiling point temperature is lower, only a certain kind of tea. Are you familiar with that?
No. Okay. I just want to figure this out.
What's that?
Who figured this out? I don't know.
White tea, green tea. Green tea, so I mentioned 97, so I might have been like off. Because this is kind of showing you, what else is this showing us? Colorado, is it, well, I might not have been too high. Colorado, you go up a little bit higher, Colorado, Matterhorn, Canada, Mount Everest. So dang, Mount Everest, your water's going to boil a lot. Yes.
One thing I noticed is, those hand warmers that you shake them up when your air activated. Mm-hmm. At like 20,000 feet, they won't work. They won't work. Because there's not enough oxygen. Mm-hmm. That makes sense because they rely on oxygen. Like when you really need them.
I think they get warmer if you leave them in your pocket.
They do.
Like, don't touch them.
They do because it's like you're there in your gloves and you're not getting as much air.
Could I go to the track meets and I have them in my coat pocket and I don't touch them? But one left in my coat pocket and one I had out and it was in my hand and in my blanket. And this one was freezing cold, but the one in my pocket was on fire.
And I think 1 in 3 are just defective.
Oh,
not very good.
Well, that's not good if you're counting on it to work. Oh. Well, so pressure cookers do this. Well, I have to change this a little bit. Of course, pressure. You guys talked about lids, and actually, a pressure cooker is a sealed sort of thing. And what it does then is as your water evaporates, it actually creates a crazy sort of system where you have high pressure. And at high pressure, that means you're going to have to, your boiling point temperature is going to be really high. What's that?
It kind of scary noise, it's going to blow up.
Mm-hmm. Old-timey ones had kind of this release valve sort of thing. And it kind of clatters and it's kind of scary. Yep. So increasing elevation decreases atmospheric pressure. So what's the word there? Which will decrease the what temperature of water? I think boiling point. Boiling point is decrease the boiling point temperature of water. Similarly, the pressure inside a pressure cooker creates an environment where the water boils at what would be the word there? Higher or lower? Higher temperatures, yep. Yep. Similarly, increasing the pressure inside a pressure cooker creates an environment where water boils at a higher temperature. Watch out. which makes it scary when you start to crank it down because you figure you have the steam to come out and that's very hot. So I got this off the figure off the internet, so you know it's right. But these are in units of bars. So in other words, so 0.5 bars above the pressure of the atmosphere, you're talking about 7 pounds per square inch above the pressure of the atmosphere. By the way, pressure of the atmosphere in PSI runs about 14. So atmosphere ATM is about 14 PSI. So in other words, you're about 50% again as much as regular. Okay.
So are you actually at 21?
Yes. Yeah. That's how I get it. So you're at 21.
So your tires are actually like 40.
So yeah. So the tires run about, yeah, they say it on the side, about 40 PSI. So it's more than the atmosphere right there. And then you can see the increase in the temperature of the boiling point. If you about double the pressure from atmosphere, that's not a whole lot more, you know what I'm saying? Instead of 100 degrees Celsius, 120 degrees Celsius. So, and I'm really not sure how much pressure you get in the pressure cooker. But the other table I got, I just grabbed one. It has some cooking time. So higher cooking temperatures means what? Is it shorter or longer cooking times? Shorter, yes. And that's actually what this does. Is it shows you, for instance, if we pick on lima beans, usually it would take you an hour and a half and it only takes you 30 minutes. Okay, black-eyed peas, an hour and a half, 20 to 30. Red beans, it would take you 3 hours and it's knocked down to about 30 minutes. We joined the bandwagon and we've got a pressure cooker at home now, but it's called an Instant Pot. So a lot of people do. What's that? Canning? Yeah. Well, that's cool. That's impressive.
Otherwise, that's scary.
I can't remember early on we talked about chemical or physical changes, but in the kitchen or in preparing food, we have both physical and chemical properties, or physical and chemical changes going on. Physical, just to kind of remind you, physical things or physical changes can be reversed. Can be reversed. That's the way I remember it. And a chemical change, whether it's in the kitchen or the chemistry lab, this is new substances. We get literally new substances are formed. It can't be reversed. Yep. Cannot be reversed. Yep. Sometimes it's easy. Sometimes it's hard to tell. And for example, you cook an egg. Okay, something's going on there. And as far as I can tell, you're not going to get your ooey gooey egg back. So this actually must be a chemical change happening to the egg. First law of thermodynamics is the word there. And it makes sense. In this universe, the energy you have has to go somewhere. So energy can't be created or destroyed. And energy will always go from a hotter place to a cooler place. So that's why, whether it's a pressure cooker or a regular thing, if you have boiling water, okay, and then you go ahead and put in your mac and cheese is cooler, right? Okay? So thermal energy is going to go from your hot water into your mac and cheese. It just is. All right. And one of the things I'm thinking I want to do the lab tomorrow actually is kind of a little bit related to this. Okay. But kind of from left to right is showing you a little bit what is happening in an egg. But before we get the egg, of course, you need something to fry your egg in. So you put your butter or margarine in. Now that actually is when you melt your butter or your margarine, can you see where that's reversible? It's reversible because you can solidify that. But when we do this to an egg, then that's not reversible because we're actually breaking intermolecular, we've talked about intermolecular bonds. This folding, and this is a little bit out of my personal biology, but this folding, and maybe you guys know more than I do, this folding actually has little bonds that specifically makes it do what it does. And then what we're doing when we're cooking is we're breaking them, and it looks like we're breaking the intermolecular bonds. So I have a little video to watch here.